All right, I called this lecture 58, but I'm not sure it's actually that number, but there it is. Okay. The first thing before I really wanted to get into it is to mention a kind of problem here involving a line integral again that somebody asked about. Okay, suppose I've got a particular vector field given here in two space in the plane. F of xy equals x plus y, comma, x minus 2y. Okay, so you can see the I and j components here. Okay, you want to compute this integral, the integral over c, f dotted with dr. Okay, dr is of course what? This. Okay, differential changes in the position vector. So that is dr. Notice the angle brackets here. And here's my f. So if I was to actually take the dot product of these two, do you see here, I would get this. Okay, and we're integrating over c. What is c in this particular case? C is supposed to be a curve composed of two straight line segments. Of course, here we're going in a particular direction. It starts at 0, 0 and ends at 1, 1, and then goes from 1, 1 to 2, 0, okay, as drawn here. Okay, so what I did was if that is indeed a straight line here, I found an equation for that line, which is simply what? Y equals x, okay, y equals x. And then the straight line from 1, 1 to 2, 0 looks like this, okay. Y equals 2 minus x here. And I'm going to use x as a parameter here. You could use t as if you want here. I'm going to have increasing values of x here. Okay, so the way it's supposed to be traversed is, notice the direction of the arrows is increasing values of x on both of those curves. Okay, so I could break the curve, what I'm calling C here, into two pieces, maybe C1 and C2. Okay, x is increasing on both of those to give those particular directions of those arrows. Okay, the way to do this, to work the problem is, go ahead and integrate over C1 and then integrate over C2 and add the results together. Okay, so just to show you how you did that, here, when you're going over C1 first, which I've marked off in these blue square brackets here, to go over C1, here's what you're going to do. Y is equal to x, right? So here, if I'm going to be parameterizing everything in terms of x here, what you could do is where you see the y here, right? You're going to replace that by, see where I've got the y there. I'm going to be replacing that by x. And here I'm going to be replacing that by x, right? And I'm going to be replacing that by x because y equals x everywhere along C1. Okay? So that becomes this, x plus x dx plus x minus 2x dx. X is going from what? 0 to 1 along that particular curve C1. Okay? And then you're going to do something similar here. In in the second curve, C2, y equals 2 minus x. So here I'm replacing y by 2 minus x, so that becomes that there. Dx is still dx. Here I'm replacing y by 2 minus x also, so that gets replaced right there, do you see? And then dy, what would that be over that curve y2 or C2? It would be negative. Notice the negative sign on that one, negative dx, okay? So I went ahead and that's what you would write for your integral here. Oh, wait, I forgot x for the C2. X is going from 1 to 2, isn't it? Okay, x is actually going from 1 to 2. You work that out and I got the answer 2, and I hope that's right, okay? Alrighty, this is not the main thing I want to discuss in this lecture though. We want to talk about divergence and curl of a vector field. Okay, first thing I'm going to do is introduce something called the del operator. Okay, that's an upside down triangle or upside down delta. Okay, it is this operator. Okay, it's I times the partial derivative with respect to x plus j times the partial derivative of y plus k times the partial derivative of z. Some people will write that with the angle brackets and the notation also. Okay, you could do that. That would be just fine. Okay, now it operates on things. This sitting by itself is is nothing, right? It's got to operate on something. Well, what happens when it operates on a scalar function like f sub x, y, z? Okay, so this thing will hit that, and where it's going to happen here is when it hits that, where I see an empty place right here, right? That's going to be filled in by what? F. Okay, so that's going to be filled in by F there. Okay, once a place where that's empty right here, that's also going to be replaced by F. And where I see empty here, that's going to be replaced by F. And you see what we end up getting here? What do we end up getting? Something we should recognize. Do you recognize that thing? Yeah, that's the gradient of F. Okay, so del of F, you've seen this notation before, but not in this context, but that is the gradient of F. Okay, now this is what? A scalar field. Okay, that's a scalar field. I want to talk about vector fields. Okay, so vector fields are going to have what? I, j, k, and components. So let's say I've got this F bar here. Okay, so I've got that. And then I'm going to have what? A function of x, y, and z, which I'm calling m. A function of n, x, y, and z, n. Darn it. And then what? Also p. Okay? And these are going to be the various component functions making up f bar. Okay? Now we could talk about something they call the divergence of f, which is sometimes written this way also. They're written both ways that you see here. But let's consider this and just be formal about it. What about a dot product of two vectors? What would you do? Okay, what? Well, this is what happens here. This is actually a scalar valued function. This ends up being the what? This operates on the m. Remember, it's like a dot product. This guy would operate on that. And this guy would operate on that, right? Remember, when you take a dot product, it's like multiplying the corresponding components and adding them up, but you're not really multiplying. You're actually having what? This operating on this operating on this operating on that. So anyways, you end up with this. And here with our subscript notation, that would be m sub x plus n sub y plus p sub z. Okay? Okay, so people will do this. And that's what we call the divergence of a vector field here. Let me maybe erase this here. That's the divergence of that vector field. It's a tendency to diverge away from a point. Okay? Tendency to diverge away from a point. That's the value of this thing at any particular point. Okay? Right now, we're not concerned with our interpretation of it. We're just going to be formal about it for now. Okay? We'll talk about what it really means later. Computing it is easy. Okay? Let's talk about another thing called the curl. Okay? The curl of f is the tendency to swirl around a point. Okay? I guess I didn't write that here, but this is a tendency to swirl around a point. This is a vector. We sometimes write it this way, del cross f. Well, you remember how to take a cross product here. We're going to do something that's going to be kind of similar. So we're going to be formal. Remember when you're taking a dot product, you consider it what? We were writing it as, although we did use a shorthand notation, you could consider it like a determinant where I've got what? I, j, and k across the first row here, right? Okay, you could consider that. And then in the second row, the components, quote unquote, of the first vector. And those are what? Just these empty operators taking partial derivatives, right? Okay. And then the last row in your quote unquote determinant would be what? The components of the second guy, right? Okay, so we would get that in there. And just dealing with this formally then, what would we end up getting? Let's maybe erase that. Okay, what we get? Well, you remember how to take a dot product, right? Okay, let's maybe do with the first one here. What would be the I component? It would be the product, quote unquote, of these two minus the product of these two. Of course, when you take the quote unquote product of these two like that, it's actually what? This operating on that. Okay? So that's the partial derivative of p with respect to y. And then you do the same thing here, only subtraction, the partial derivative of n with respect to z. Okay? So that's what you end up getting when you do this. Okay? Alrighty. And then what? Plus, remember how it goes? Here you gotta get these in the right order. You take the partial derivative with respect to z, it operates on m, minus the partial derivative of p with respect to x, okay? If you don't like to memorize it in that order, well, that's okay, but that better be a minus sign there, okay? Either way, remember, a lot of people were having difficulty in finding a cross product that we're getting the wrong signature in the middle on the j component, in other words, okay? Make sure you get that right there, okay? All right. And the k components, you do likewise there, okay? All right. Let's go ahead and work a problem for some, just sort of a simple field here. Suppose I've got this particular vector field. F bar is yz, xz, xy. Okay? I claim the divergence would be 0, and the curl would also be 0. The divergence is what? A scalar, though. And the what? Curl is a vector. Okay? We'll talk about more of these in greater depth later. Okay? So work out the details of this. It's very easy. Here we could do on our heads partial derivative with respect to x. That'd be 0, because x, y, and z are independent variables. The other two are always being held constant and are differentiating with respect to whatever independent variable. Okay? So that with respect to y would be 0. That with respect to z would be 0. And we would get 0 for a total here. Okay? The second one's maybe a little harder to see here, but we would be doing what first? We're differentiating that with respect to, in the first one, differentiating with respect to y, and then subtracting that with respect to z, and you would get z minus z. Oh, wait, I guess I'm wrong on that one. Okay, here, let's come back here. Okay, what would you actually get here? Let me write this one out here. Okay. If you don't mind, or even if you do, I'm going to use our little shorthand notation here. Okay, so I'm going to go like this. Oh, I know what I'll do. Let's come back here. Just erase this. Let's do it this way here. Okay, let's do it this way. Okay, let's go ahead. Okay, what's our P? Okay, P with respect to y, what are you going to get there? You're going to get x, and subtract this. Our n with respect to z, what are you going to get? You're going to get x. Okay, all right. Now, let's maybe erase those. Okay, now what? M with respect to z, m with respect to z would be y, minus p with respect to x. That would give us y. Okay, so there we've got that. Let's maybe erase those now. And then what? N with respect to x, so that would be z, minus m with respect to y, that would be z, and we get 0. Okay, so these both happen to be 0 for this strange field here. That's unusual. Okay, that doesn't usually happen. Okay, so a strange example here. Why are we interested in actually, computing for now, the curl or the divergence here? And in fact, we're going to actually be focusing on the curl here in a little bit. Let's talk about conservative fields and potential functions. We'll talk about the relationship that it has with stuff like curl. Okay? What does it mean to be a conservative field? Okay? I mention this because you folks shouldn't have any difficulty computing. There's one section in your textbook where they ask you to compute divergence and curl. It should be easy. Okay, I'm not going to spend a lot of time on that. If you can take partial derivatives, you're in good shape, right? All right. Conservative fields and a potential function. F is a conservative field if it is induced by a scalar function. In other words, if there actually is a scalar function, f of x, y, z, or possibly just f of x, y if you're dealing with a plane, okay, such that the scalar or the vector field is actually the gradient of that scalar field, okay, or that scalar function if you wish, okay, if there exists such a thing. Many times one doesn't exist, okay, but if there does, then we call that thing a conservative field, okay, because a conservative field has special properties, as you might guess here, that are going to be really nice for computing things like line integrals, okay? Now, I might mention here that this has to be true not just at some point, but all points of the vector field f bar, okay? If there does exist such a function, a scalar function here, we call that function a potential function for the field. You ever heard of electrical or gravitational potential? Those are scalar valued functions if you know anything about them, right? Okay. Yeah. I might mention now that the static electric field is a conservative field, as is the gravitational field. They are induced by a potential function. Okay. Now, let's talk about a particular example here. Okay? So I said I've got this following field. Again, this is just going to be a function of x and y, as you can see. E to the x times the sine of y, e to the x times the cosine of y. I claim that this is a conservative field. Okay? What would that mean? Well, I claim that there is a scalar function, right, a function of x and y, such that the gradient of f actually is equal to this guy up there. Okay? You ready? How do I know that? Well, I'll explain how I know that. But right now, I would say because the curl of this is 0 everywhere. Okay? Because the curl of this is 0 everywhere. In a case like that, you know you're dealing with a conservative field. We'll have theorems being a little more explicit about that stuff later. But right now, I'm going to prove it more directly. I'm going to actually find this potential function for us. Now, here's the idea. I'm looking for a function f of xy such that what? Its gradient yields this, right? Now, what's the gradient? Remember, the gradient of f would simply be this. The field f sub x, f sub y in 2 dimensions, right? So that would mean my f sub x would have to be what? E to the x sine of y, and what? My f sub y would be e to the x cosine y. Okay, you can see I've written out that stuff right there. That's what I would be doing, right? But that's what I would be attempting to do. Okay? Now, how can we do something like that? How could we find such an f? Okay? Well, later on we'll run it through this curl test that I mentioned before we even start. But since we don't have that test right now, I'm just going to go ahead and show you how to find it. If it doesn't pass that curl, if the curl isn't identically 0 everywhere, we wouldn't even start this process, is the idea, because you'd be seeking in vain. Okay? But right now we don't care about that. I'm just going to show you that I can actually find a little f that'll work for us. Okay? Anyways. Okay? So the derivative of little f with respect to x is supposed to be what? E to the x sine of y, like I've just circled right there. So what I'm going to do is integrate e to the x sine y with respect to x. Now, not everybody likes that notation there. Okay? But I'm just emphasizing that I'm doing a partial differentiation. Now, I didn't really use that notation before, but we should get together and vote with this. Actually is a good notation in my opinion. Okay? But anyways, so basically I'm going to integrate with respect to x. What does that mean with a partial integration? That means I'm holding y as a constant, right? The other independent variable. Okay, so just do that. Okay? And you see what I would get? I would be basically just integrating e to the x with respect to x. Holding y as a constant would be like holding sine of y constant, right? So what would I get? I would get e to the x sine x. Now, usually when you integrate, you end up with what? Plus c, right? But I claim, because we're doing just partial integration, in this case with respect to x, we don't really get that. Instead, what we should have at the end is any function of y. Think about it. Any function of y differentiated with respect to x should be what? 0, because I'm doing partial differentiation holding y as a constant in a case when I differentiate with respect to x, right? So in fact, I say here, don't just add c, add g of y, where g of y is technically any function of y. Okay? Does that make sense? Okay, I hope so. Now, so what I'm saying now, what I've done here, what I've done is sort of found a partial form for my little f. Okay, I found a partial form for my little f. Now, different people take different approaches in doing this, but this is the approach I'm going to take in doing this. Everybody starts out the way I've done here. But now this is what I'm going to do. Now, you remember from our condition here that the partial derivative of little f with respect to y is supposed to be what? E to the x f sub y, right? That's this condition right there. Okay? I haven't even talked about that yet. Let's talk about that now. Well, here's my reasoning. If f sub x has this form right here, okay, if I took the partial derivative of this with respect to y now, what would I get? I would get, well, the partial derivative of that with respect to y is just e to the x. This would be what? Cosine, right? Cosine y. Okay? So I would get this. And what would be the derivative of this with respect to y? It would be g prime of y. This is a whole function of y, right? So even if I take a partial derivative of f with respect to y, this ends up being a whole derivative. It ends up being g prime. Now, I say here this is given, so these two things should be equal, right? Which I've drawn here. These should be equal. That would imply what? If I equate these two, hey, these match up. That's perfect. That's perfect. What is my g sub y actually equal to? I should say g prime of y equal to. That means g prime of y would be 0. That means g sub y would be any constant. So a potential function for this is what? F sub xy is e to the x sine y. So if I take any function of this form, take its partial derivative with respect to x, I would get e to the x sine y, just like I want. And what? If I take its partial derivative with respect to y, I would get what? This, e to the x cosine y, just like I want. Perfect, okay? Any C will do at the end of this. So there exists a potential function that actually induces this particular field. Okay, this particular, I'm trying to write here. This particular gradient field. There indeed exists a scalar function that induces it via the what? The gradient. Okay? Alrighty. Well, that's cool. Okay. Now, here's what I mentioned earlier here. Electric and, I should say this back then. This doesn't always work, right? There's all kinds of fields that can't be induced by what? Or that are not the gradient of any scalar function under the sun. There's simply functions like this, gradient or vector fields like this that you can take for which there exists no scalar function on the sun for which you can equate these two. It just don't work, okay, in certain cases. And we'll see when you can do this and when you can't, okay, later on. That's part of the reason why I introduced divergence and curl. First of all, see if you can get that section in your homework done. And second of all, why we would even care about such things. Okay, but let's take a look at this. I mentioned this earlier. When I say electric field, I mean static, electric, not electromagnetic here. Okay, and gravitational fields are conservative. Well, you remember both of these, what is it, Coulomb's law and Newton's law, they're both inverse square laws, right? Now, when they say the inverse square law, even though I've got a cube down here, remember in my formula that if I was to write this in terms of what, the actual magnitude, that I would end up with an inverse square law, right? Okay, because I've got r right there. When I take the magnitude of r, that would cancel with the cube of the magnitude of r and give an inverse square. Okay? Alrighty. Man, I really messed this up, so let's take this off here. Okay? Anyway, I'm going to show you that these are in fact conservative fields, and I'm going to show you that by actually giving you a potential function for these. Okay? All right, so both the electric and gravitational field have this general look to them. The k's are different, right? But it's some constant times the position vector, and this constant could be negative or positive in the electric case, but divided by the cube of the magnitude of the position, right? Okay, anyways, so we've got that written there. Okay? Now, I claim this is a potential function right here. This fellow right here is a potential function. Negative k divided by the magnitude of r bar. Okay? Here's r bar. This is a potential function, I claim. Well, how would I show that? Well, I would find the gradient of this thing, right? And show that it leads to that fellow. Okay? That's what I would do. Okay? Okay, let's do a bunch of erasing again. Okay, I'm getting really messy here. Here's another thing I can do. I can make a big eraser so it looks more like a blackboard eraser. Erase more at once here. Okay? Alright, having fun erasing. Now, let's get back here. Okay, how would I show this? Well, let's take the partial derivative of this thing with respect to x. Okay? First thing you would do, you're going to use a chain rule, right? This is what? Negative k magnitude of r to the negative 1 power. So you're going to use the chain rule, so it would start out with a power rule, really, right? The negative 1 here would multiply in the negative k, yielding the plus k, and then you'd subtract 1 from the exponent, and that would be the minus 2 power, which I put downstairs like that. And then don't forget, with the chain rule, you'd have to multiply by the derivative with respect to the inner function here. That would be the partial derivative of the magnitude of r with respect to x. Okay? Alrighty, so that's how that's coming out. Alright. Okay, well that part's easy. Now we need to deal with what? This part right there. Okay, now what's the magnitude of r? Well, what's the magnitude of this thing? That's not hard. It's what? The square root of the sum of the squares. So you've seen this before, right? That. I got to take the partial derivative of that with respect to x. That doesn't look so bad. Once again, I've got to use some power rule and chain rule and stuff. But this is going to be what? Well, you think of it being to the half power, right? That's being raised to the half power. So I put the half out front. Okay? I subtract 1 from the exponent there, and I get to the minus half power. So that's what? A square root only downstairs in the denominator, like that. And then I multiply, once again, chain rule, multiply by the partial derivative with respect to x of the inner function. Since y and z are independent variables, they're being held constant, and I would get just what? 2x upstairs. And then put that all together, you recognize this denominator here as actually being the magnitude of r, right? Only it's downstairs now. So put it all together, what do you get? You get kx over the magnitude of r cubed. And now you can see from the symmetry of the situation here what results you're going to get if you take the partial derivative with respect to y and z. It's going to be almost exactly the same thing, only in place of x, you're going to have what? Y and z respectively. And if you put them all together in a vector then, you see that you're actually going to get kx over magnitude of r cubed, ky over magnitude of r cubed, kz over magnitude of r cubed, which can be written more compactly this way, which is really this thing, which is our original, here, let me take that off there, I blurred it, which is our original F. Okay? Hey, electric and gravitational fields are conservative fields. Some people call those gradient fields also, because it means what? That the vector field's been induced by the gradient of a scalar function. Okay? Alrighty. So there we've got it. Here's the conservative. I'm going to end here, but let's mention the conservative field test. Okay? Remember how I said before, when I was working some of those problems, I just blatantly said it was a conservative field and then looked for what? The potential function. Before you would ever start doing that, you would really like to know whether it's conservative or not. Because if it's not even conservative, you wouldn't even bother looking for the potential function, right? Okay, well, I've circled this here, this conservative field test. Okay, let's say you've got a particular vector field, okay? And now I'm doing this in 3 dimensions, okay, so the most general case, but the same thing holds in 2 dimensions, by the way, everything I'm going to state here. But I'm going to call the I component M, the J component N, and the P component, or the K component P, and those are functions of x, y, and z, right? Those are scalar functions of x, y, and z. So M is really M of x, y, z, and so forth. Okay, these are actually scalar valued functions. Okay? All right, suppose that these are continuous in some simply connected region. I'll explain that in a minute. R of r cubed or r squared. F is conservative if and only if its curl is identically 0. Okay, I should really say this. I should go to black here. Identically 0. I mean, it's curl 0 at every point in the region R. Okay? Now, we need to talk about simply connected region. Okay? But this is going to be, we're always going to be using simply connected regions. So basically, when I ask you guys questions about this, you're just going to compute the curl, okay, and see if it's identically 0. Okay, compute the curl and see if it's identically 0. Okay, and I have a typo here, don't I? What should I have here? The curl is a vector, right? So here, let me erase just a little bit here. I have a typo. Maybe I'll come over here and do this then. I'll go to this, and I'll go to black. Do you see the typo? Okay, this should be what? Should have a bar on top, shouldn't it? Yeah, that's a vector. Okay, that's a vector. Alrighty, let's talk about what this means to be a simply connected region. Now, I've actually got this backwards here. Let's talk about a simple closed curve first. You know what a simple closed curve is? Okay, a simple closed curve is a curve that can be obtained by a one-to-one continuous deformation of a circle. It's a topological circle is what we would say in higher mathematics. Basically, it's something that you can draw that's very circle-like, even if it is a crappily drawn circle, okay? Poorly drawn circle, okay? These are all simple closed curves, no matter. Okay? Do you see all those are screwy circles? Okay, messed up circles. What's not a simple closed curve? Well, something like this, a figure 8 here. Okay, a figure 8 is not simple. It's closed because you could imagine tracing it around and coming back to your original starting point, but it's not simple because it crosses itself here. You see it crosses itself? This is a simple curve here. Okay, it's not closed. You don't get back where you started. It doesn't cross itself, but it's not closed. There could be curves that are closed but not simple. For example, something like this. All right. So just think of a messed up circle when you think of a simple closed curve. Or, well, I guess a circle that's not messed up would also be one. Okay? A simply connected domain is a path-connected domain. What is a path-connected domain? All these technical things. A path-connected domain is where you can, from one point in the domain to another point in the domain, you can always find a path that stays within the domain all the way through. So one that would not be path-connected here would be something like this. Okay? Do you see if my domain is these two, the union of these two red balls here, I can't go from here to a point over here without passing through what? Regions that are not part of the domain there. Okay? So this particular thing would not be path connected here. Okay? Anyway. Where one can continuously shrink any simple closed curve into a point while remaining in the domain. Okay? This is simply connected. Here's the idea. If I have any simple closed curve in here, I can shrink it continuously, that's supposed to be closed, shrink it continuously down to a point. Can you see that? Okay, I could shrink that continuously down to a point, staying in the domain the whole time. Okay? I'm going to change my color here. Let's do this. Okay. In this one, this is not simply connected. Yeah, there do exist simple closed curves that I can shrink down to a point continuously, but there exists some that I can't do that to. Do you see this one? Well, I didn't draw that very well. It's supposed to be inside there. Okay. Do you see that, how it goes around that hole? Okay. If I try to shrink that down to a point, I can't do it without what? Leaving the domain. Okay? What does simply connected mean in 2 dimensions? It means no holes. That's all it means in 2 dimensions. It just means no holes. So if I come back here to my theorem, where I'm talking about this, my conservative field test here, you can just think of this as a domain. If I'm talking about 2 dimensions here, a simply connected region, if I'm talking about R squared here, it just means there's no holes in R. No holes in R. Okay, that's all it means in 2 dimensions. In 3 dimensions, it still has the same definition here, but it's a little more complicated here. You see what right here? Look at these are simply connected here. Do you see how I could have a simple closed curve and shrink it to a point inside that sphere? I could also do it right here. Oh no, it surrounds that open sphere. See how there's a little open sphere inside? It's been gobbled out in the middle. No, I could still shrink that thing. Think about it. I could shrink that thing down to a point without having to pass through that circle because I have a little wiggle room, right, inside that sphere. So long as I stay outside that, when I'm shrinking it, just stay outside that inner sphere, and I could do it fine. Problem in these other cases here. Do you see here? This is not simply connected. What if I took my simple closed curve that went around this? What's wrong with this sphere? It's been drilled through. I drilled right through that sphere. If I try to shrink that down to a point, I can't do it and stay inside the domain, right? Okay? Because it's the simple closed curve I took around went right around that drilled out cylinder. Okay? Nope, I can't shrink it down to a point. In fact, there are examples where you can the curl may be identically 0 in the domain, but still not be conservative in cases like this. In both of these, by the way. This one I don't need to show. The whole thing's just a cylinder here. Topologically, this is identical to this. These two are the same thing. I will put this online though, so you can get a better look at it. Okay, this picture here that I've drawn here. Okay. So there's the idea. Oops. Wow, I messed up that thing. Oh, okay. That came back. That scared me for a minute. Alrighty. Alright, that should be enough for this lecture, I think. Okay? Simple closed curve. And that'll be enough. Alright.